Good afternoon, class. Today we're continuing along with file system implementation. Today's topics are allocation methods, free space management, and efficiency and performance. For your viewing pleasure, here are the chapter objectives another time. So we'll start with contiguous allocation. Now keep in mind that we're talking about a mechanical disk drive that has seek times, a rotational latency delay, as well as transfer delay. So contiguous allocation is just as it says, all of the blocks for a file are allocated contiguously, which is going to imply that all the blocks for a file are concentrated within a single cylinder or a small number of cylinders, which is great for performance. Very few seeks, but we'll have to deal with external fragmentation, leading to compaction from time to time, as well as what we do if the file grows to the point where we have to move it because we don't have enough contiguous space to grow it into. So contiguous allocation, the parameters for a file are a starting block and a number of blocks. So assuming that the block size is 512 bytes, given a logical address, and here we're talking about a byte offset within the file. To convert that to a physical block number and an offset within the block, take that logical address divided by 512, the block size. The quotient is the block number relative to the starting block. So take that, add it to the starting block number, and then the remainder is the offset within the block. So a file that's built with extents, rather than being a single contiguous set of blocks, is a number of contiguous set of blocks. This helps to deal with the problem of a growing file that no longer fits within its space. Rather than move it, we would allocate another contiguous set of blocks, and that would be an extent. So that the extents aren't necessarily within the same cylinder. So we may well lose some performance as we traverse between the extents because of read-write head seeks. So the next approach is linked allocation, in which each block contains at its beginning a pointer to the next block. So again, it's just a linked list of blocks. So this is similar to, if you think about it, paging, because the blocks for a file can be spread out over the entire disk drive. So that means no external fragmentation, and we won't have to perform compaction due to not being able to find a large enough contiguous space for a file, because we don't need contiguous space. We might want to perform compaction for efficiency reasons, because now the blocks of a file can be spread out all over the disk, which implies that as we go to each next block, we might have to perform a seek each time, right? With this allocation scheme, it's not necessarily the case that all of the blocks of a file are within a single cylinder. And reliability can be a problem if you lose a block pointer in the middle of the file. Then what do? You've lost a certain part of the file. Most operating systems that use linked allocation will have some sort of utility to attempt to relink the file, but how possible it is to do that, I'd say, is open to question. So FAT is a variation of linked allocation where instead of keeping the block pointers within the blocks, instead the block pointers are gathered together in some blocks at the beginning of the disk drive. So this speeds up access. The FAT blocks can be kept cached in memory. So rather than traversing from link to link to link um, by reading blocks and extracting the links, we can simply pull the links from the cached FAT blocks. So in this example, we're assuming that the block pointer for linked allocation is 1 byte long. That's kind of on the short side. That of course implies that we can only have 256 blocks, but it works. I mean, in reality, you would allocate more bytes for the pointer. So then given that 1 byte pointer, that implies that we have 511 bytes left for data within each block, hence leading to the logical address to physical address mapping of dividing by 511. Right, the quotient then is which block in the linked list the byte we're trying to access is located in, and the remainder is the offset into that block where we'll find the byte. This example here is somewhat messed up. The same figure from the book has the same problems. So here we have a file Jeep with the directory entry says that the starting block is block 9. Here's block 9. So the pointer here should be pointing instead of 1. In this case, the ones digit got truncated. It should say 16 here. And the pointer here should say 1. The pointer here should say 10. The pointer here should say 25. And 25 is the last block, so we have the end of file block pointer. So here's how that would look with FAT allocation, which you'll be working with if you do the MS-DOS file system lab. So directory entry test, file name named test with a start block of 217. Right, so in order to get at the data, we would go to block 217 on the disk drive, then look in the FAT for the next block. So entry 217 has a pointer to 618, so the second block of the file is block 618 out on disk. Then we would go to FAT entry 618 to find out that 339 is the third block of the file. And it looks like there may be a problem with this figure as well. Let's assume that the pointer entry at offset 339 is -1, indicating that 339 is the last block of the file. So the problem with linked allocation is that to find the nth block of a file, you have to chase through n pointers. And it's of course much faster to do that with FAT allocation because you're not doing disk operations, but still you have pointer chasing to do. The third allocation method is indexed allocation, in which the pointers are kept in an array within typically the directory entry itself or the inode for the file. And so finding the nth block of a file is simply a matter of indexing into the nth position within the index table. So here's what that could look like. The directory entry for a file contains metadata indicating what the index block for the file is. So that's fetched and brought into memory. and then index directly to locate a specific block within the file. So we obviously need the index table. This method makes it easy for us to achieve random access of the data within the file as opposed to sequential access, simply because we have the block pointers all together indexed for us. Imagine using linked allocation and accessing a file randomly. You're going to take a serious performance hit there. Of course, index allocation potentially has the same problem linked allocation does, in that the blocks of a file can be scattered over all the cylinders of a disk. So once again, we don't have any external fragmentation, so we don't need to perform compaction for that reason, but we may want to perform compaction for performance reasons in order to try to bring all the blocks of a file within the same cylinder. The logical address to physical block and offset calculation is fairly simple. Take the logical address, divide by the block size. The quotient gives you the index into the index table, and the remainder gives you the offset within the block. It's certainly possible, if a file is large enough, that a single index block won't be sufficient. One way of adding additional index blocks is to link them. So the index blocks, the first byte, again, we're assuming that a block pointer is a single byte. That first byte is a pointer to the next index block, giving this logical address mapping, because now we have a two-layer map in essence. Right, first we have to find the appropriate index block and then find the file block. So the divisor here is 512 bytes, because that's the size of a data block, times 511, which is the number of block pointers within a single index block. So this quotient gives us the linked index block that we want. The remainder then is going to be contain both the index within that index block as well as the byte offset. So taking that remainder and then dividing it by 512, the number of bytes within a data block, gives us the index into that index block, and then the offset the offset into the final data block. The problem with this approach, obviously, is that we have to chase those links, assuming that we're not keeping the index blocks cached in memory. A way of fixing that problem is to use a two-level index, as we saw with paging. So in this example, which is different than the previous examples, and I'll stick with these numbers. So now we're magically assuming that data block is 4K bytes, and that the pointers now are 4-byte 32-bit pointers, and this is a two-level index scheme, as we've seen. So that implies that we can have bytes or files of up to size 4 gigabytes. Now, these numbers here are incorrect. This first number should reflect the size of a data block, so that should be 4K. This number should reflect the number of pointers in the second level index, so that would be 1024. The quotient then will give us the index into the top level index table, and the remainder then will give us the index into the second level table, right, which will give us the data block and also the offset within that data block. So this remainder is applied here. Again, this 512 should be the size of the final data block. In other words, 4K. That and the quotient will give us the index into the second level index block, and the remainder then is the byte offset within the data block. So here's an illustration. Right, starting from a logical address, we have the outer index, the top level index, and then a set of index tables. Each of these is a single block, and the pointers here are pointers to the actual data blocks of the file. Unix's UFS uses a hybrid scheme. An inode contains a certain number of direct blocks. So this is a single level index, which works great for smaller files, yields quick access for larger files. Then after the direct block pointers, there's a single indirect pointer, which you can see is a two-level index table for even larger files, and there's a double indirect pointer, which gives us the single indirect gives us let me go back. I'm forgetting about ignoring the direct blocks here for a moment. The single indirect is, in a sense, the index allocation that we were talking about originally, and that this is a pointer to an index block. For larger files, the double indirect is a pointer to an index table of index tables, as we saw with the last example. And for the largest files, there's a triple indirect pointer. So purely on performance, contiguous allocation is the best for both sequential and random access because all the blocks are going to be restricted within a single cylinder or a small number of cylinders. Linked allocation is good for sequential access. We say only good because we may have to perform disk seeks if the blocks of the file are scattered throughout the disk cylinders. It's not very good at all for random access. Index can be a little more complicated, as you remember from our discussion of paging. We have to worry about effective memory access because of having to read a page table entry before getting to the actual memory access. Indexed allocation has a similar issue. A two-level index could require two index block reads and then the data block read, and of course more than likely the operating system would make use of caching techniques to try to keep index blocks in memory. Clustering is the notion of merging contiguous blocks into a cluster of blocks to help increase the amount of data that can be brought in before the necessity of performing a disk seek, for instance. I'll skip this, except to say, given the several order of magnitude differences between CPU speed and disk speed, it can be a big payoff to execute a lot of CPU instructions in order to avoid moving the disk's read-write heads. There are a number of techniques for keeping track of the free blocks on a disk system. One method illustrated here is a bitmap where a single bit within a byte is set to 0 if the block is being used, otherwise it's set to 1. This illustrates the potential size of a bitmap block, assuming that we have a disk block size of 4K and a terabyte disk drive. Then we have 2 to the 28 bits, which is 32 megabytes. If we cluster the 4K bytes into clusters of 4 blocks, then the bitmap goes down to 8 megabytes. And if we're trying to do contiguous allocation, it's easy to examine the bitmap to determine where contiguous sets of blocks exist. Alternatively, we could simply link the free blocks together. This gives us the bitmap is overhead that has to be stored somewhere. A linked free list such as this doesn't require such storage overhead. Of course, trying to determine where we might have contiguous blocks is going to be more complicated with this simple scheme. So improvements include grouping, which rather than within each free block keeping a single pointer to the next free block, of filling each free block with as many pointers as possible in order to collapse the length of the free block list, and also counting. So in addition to the link to the next free block, include a count of the number of contiguous free blocks that will assist with performing contiguous allocation. Of course, coalescing adjacent free blocks still needs to be performed. I'm going to skip this slide. We've already discussed efficiency and performance a fair degree, so I don't see anything to add from this slide. There's some important information here. As I've kind of been implying, the file system will cache blocks in memory. When performing writes, blocks being written can be cached. Of course, one runs into the problem of if the system crashes before that data is written, how do we know that, what is the exact state of the file system then? These free behind, when performing sequential access, of course, once you've moved to the next block, the block that from which you just moved, you can write and remove from cache immediately, and then you can also, anticipating the next block read ahead because of these caching techniques. Writes can be faster than reads, unless of course you're performing a read ahead technique for reads. I'll skip this slide, which means I'm skipping this slide, and skipping this slide, and skipping this slide, and that completes today's material.